Penguin Random House Audio presents The Dream Universe, How Fundamental Physics Lost Its Way, by David Lindley. Read for you by John Lee. In memory of Gwen Lindley, 1924 to 2011. Preface. Almost 30 years ago, I published my first book, The End of Physics. You will no doubt be aware that there is still plenty of physics going on, but my focus in The End of Physics was more specific. I was discussing fundamental physics, the discipline that deals with the nature of matter at its most elementary level, the origin of the forces that hold matter together, and the formation of the universe itself. At the time, in the early 1990s, many scientists were all fired up about the possibility of building a theory of everything, a single coherent intellectual framework that would capture all of fundamental physics in one neat and satisfying package. The point of my book was to say this ambition was delusional, because such a theory could never be adequately tested. No telescopes or particle colliders, I said, would ever be powerful enough to see the finest internal details of the various proposed theories of everything, so that the connection between what the theories said and what we could actually observe and test was at best a lengthy and tenuous chain of inference. I subtitled my book The Myth of a Unified Theory. By myth, I meant that if physicists took a certain theory of everything to be the one true theory, it would not be because they could prove it right. It would be because they had collectively decided that it did a good enough job, that it was the best that could be reasonably achieved. But I was skeptical that even this lesser ambition could be realized. It's impossible to imagine the community of theoretical physicists ever coming to the conclusion that they had done everything they could possibly do, that they had run out of questions to ask, and that it was time to close down the store and take up lawn bowls. In one respect, what I said in The End of Physics proved correct. The very phrase, theory of everything, is little heard these days, and then mostly in a tone of knowing irony. The theorists who continue to ponder fundamental questions about our universe have largely embraced a very different but equally grandiose idea, that of the multiverse, an overarching conception that says that all kinds of possible universes exist in some parallel fashion, that our universe is one of many, and probably nothing very special to boot, and that what counts as fundamental physics will differ substantially from one universe to the next. It was, no doubt, a great overreach to imagine that physics could ever account for every last jot and tittle about the construction and contents of our universe, but now the quest appears to have gone to the opposite extreme. According to the multiverse hypothesis, the answer to pretty much any question about how or why our universe looks the way it does is that there is no answer. In our universe, things look like this, but in some other universe they look like that. That's quite a come-down from the extravagant hopes of just a few decades ago. And it raises a challenging question. What, exactly, are scholars of fundamental physics today trying to achieve? If their theories have no specific explanatory power when it comes to our universe in particular, then what larger question, if any, are they trying to answer? This new book, The Dream Universe, is my exploration of that question, and it comes to some conclusions that few physicists working on fundamental and cosmological issues will be happy to hear. When I wrote The End of Physics, I had only recently emerged from my own professional immersion in research, working at Cambridge University and then at Fermilab on the connections between particle physics and cosmology. When I left academic research and decided to write about science rather than practice it, I became fascinated with the history of science. Since that time, I have written a number of books with an overtly historical perspective. My exploration of the scientific past has now come full circle and brought me back to my old subject, the state of modern, cutting-edge, fundamental physics. Reading and writing about history has taught me something that barely crossed my mind when I was practicing science, namely, that the idea of what a good scientific theory ought to look like is not set in stone, like some kind of ancient commandment. It is, instead, a matter that exists in the scientific atmosphere of its time. It is the common sense of its age, the unspoken ideal that scientists take for granted but think little about, and yet it changes profoundly from one era to the next. That's why I chose to begin the dream universe with the story of Galileo Galilei, who laid the foundations for modern science by demonstrating that an astute combination of observation and reason could reveal how the natural world works. Galileo, as everyone knows, was condemned by the Church for his heretical views. But in the first part of this book, I dig into the true source of the Church's opposition, which was not primarily theological, but rather philosophical, reaching back to the thinking of the ancient Greeks. In doing so, I look at the Greeks' contribution to science. They were enamoured of reason and logic, certainly, and they greatly esteemed the theorems of geometry. But for the most part they either ignored or positively disdained the sort of knowledge that could be gained by looking closely at the world they lived in. Measured by modern standards, what the Greeks espoused as an understanding of the universe at large was a form of idealistic philosophy very different from how we now conceive of scientific physics and cosmology. Only by breaking the hold of that ancient orthodoxy was Galileo able to think in a recognizably modern way. In particular, he used mathematics in a new way, not as a source of fundamental truths about the world, but as a tool to manage the truths that observation and experiment delivered. I delve into that notion in the second part of the book, which looks at how scientists of the classical era, up to the end of the 19th century more or less, deployed mathematics with ever greater sophistication, but thought of it always as a means of understanding the world, not as an arbiter or provider of fundamental truth. That attitude began to change with the dawning of the 20th century, as physicists sought to explore a world of fundamental phenomena increasingly removed from direct experience. In the third part of the book, I look at the rise of particle physics and modern cosmology, and argue that while the power of mathematics has been essential in delivering deep theoretical understanding, it has also widened the gulf between theory and observation and, at times, led astray scientists who put too much faith in what mathematics tells them. Those arguments set up the final part of the book, in which I assess some of the more extreme trends in fundamental physics and ask whether practitioners of this discipline can truly be regarded as scientists in the old Galilean sense. I conclude that, in fact, they have reverted to a pre-modern way of thinking about the universe in which, whether they acknowledge it or not, they expect that mathematics alone will provide all the answers. Fundamental physics has evolved into a version of philosophy, a highly mathematical form of philosophy to be sure, but one that shares with other areas of philosophical inquiry an endless capacity to ask deep questions and an impressive inability ever to answer them. Part 1. How Science Began. What we understand today as the scientific method of inquiry began during the Renaissance in Europe, and the individual most powerfully associated with its genesis is Galileo Galilei. The story is often told simplistically as one of a free-thinking pioneer rebelling against the stodgy orthodoxy of the Catholic Church. But there's more to it than that. On matters of astronomy and mathematics, the Church's orthodoxy was not particularly Christian, but had its roots in certain branches of ancient Greek philosophy. Those philosophers are often credited with the earliest inklings of scientific thought, but that's an exaggeration. In their views on the nature of the universe, the ancient Greeks evolved their own orthodoxy, and it was by breaking free of those constraints that Galileo found the path to modern science. Chapter 1. Galileo Invents Science. A book of geometrical problems published in 1561 included an analysis of how far a cannonball would travel depending on the angle at which it was fired into the air. A charming illustration accompanied the discussion. It showed a cannonball flying from the mouth of the cannon in a perfectly straight line, then, having reached its maximum height, dropping straight down to the ground. The relationship...
Sample complete. Ready to continue?